Hey everybody, welcome to the second video of our calculus series where we will be covering both AB and BC only topics. Today we will be discussing defined and undefined limits. So if you remember from our last video, which was the introduction to limits, a limit is the value that a function approaches as we approach a specific x value or input. Today we will be discussing and looking at the specific cases where the limit does not exist and why that's so. So our first example right here is going to be a function that has an infinite discontinuity, or is also known as just having a vertical asymptote. Our first example will be the limit as x approaches 1 for the function x plus 1 over x minus 1. Now, I always think it's easier to visualize these concepts with a graph, so I think it's kind of helpful if we start off with a little quick sketch of this graph. First, we're going to identify where that vertical asymptote is, which would be, in this case, at x equals 1, and we find our vertical asymptote by using that denominator of our function, x minus 1. So I've already drawn in that line right here, and we're also going to find this horizontal asymptote as our just second guideline for the graph, which we can see would be at y equals 1. I also have that drawn in right here. So if we just follow these guidelines, we would get a graph that looks kind of like this. Now this isn't perfect, but it will serve the purposes for this example. So in our last video, we saw how we could determine a limit from a graph, which is essentially just by looking at what values the function is approaching as it gets closer and closer to the x value on either side. So if we were to look at where the function is approaching 1 on either side, so we would want to look as we get closer and closer on both sides, and we would want to look at what this looks like on our actual function, we would see that the function is not actually approaching a specific value. So what I mean is, now if we're looking at our function, I might actually change the color right here. But yeah, if we were to look at what our function is approaching as we get closer and closer to 1 from values that are greater, we would see this right here. You see, we're not actually approaching a specific value. Instead, we're approaching infinity because we have that asymptotic behavior. But now if we were to look at what the function is approaching as we get closer and closer to 1 from inputs that are less than 1, so which would be like right around here, we would see that again, the function is not approaching a specific value, but is instead going towards negative infinity, again, because of that asymptote behavior. So we have two characteristics that make this problem slightly different than the ones we've seen in the past. The first is that we cannot identify a specific numerical value for this limit because, we're seeing infinity and negative infinity. And the second is that the function has different behaviors on either side of the value x equals 1. So when we're less than x equals 1, we're approaching negative infinity, but when we're greater than x equals 1, we're approaching positive infinity. And since the function is not approaching the same value on either side, we would say that the limit does not exist for this question because the limit is what the function is approaching as we get closer to this input on both sides. And since they don't match, we would say that the limit does not exist, which sometimes you will see as just DNE, just stands for does not exist. Okay, so looking at our next example, we have the limit as x approaches 1 of the function x over ln of x. So unlike the last question, this function is not as easy to graph. But if you remember from our last video, there's a specific property that we can use of limits to make this question slightly easier, and this would be the quotient property of limits, which we can use to split this one limit into 2, making it actually equal to the limit as x approaches 1 of x over the limit as x approaches 1 of ln of x. So now we can just solve these limits separately from each other, and we can use direct substitution for each limit because the functions are continuous for the value where x equals 1. So first we'll just substitute 1 in for x on the top, which would just give us 1, and then we would substitute 1 in for x on our second limit, which would get us ln of 1. And this is just equal to 1 over 0 because the natural log of 1 is just 0. So now we know that we cannot divide by 0. So in this case, the limit would be undefined. One thing to note about questions like these is that they are only undefined if the denominator is equal to 0, but the numerator is not equal to 0. So if you would have a limit that you got an answer that was equal to 0 over 0, that would be an indeterminate form, and you would have to use some other technique to get an answer, which we'll discuss in later videos. But in our case, because we have 1 as our numerator and 0 as our denominator, we would just say that the limit is undefined. So I'm going to write that right here. Undefined. All right, our next example, we have right here, we have a nice graph for us. We're going to look at a function which has what is known as a jump discontinuity. So again, we have a graph, so we want to look at the outputs of the function as we approach the input, which in this case is 4, because we're looking at the limit as x approaches 4 for this function f of x. And we want to look as we approach the input 4 from either side. So again, this is where 4 is. So we want to look from inputs that are greater than and inputs that are less than. So now if we were to approach from values that are greater than on the function, we'd be right here. We would see that we're approaching the value 2. But now if we were to approach from values that are less than 4, which should be over here, we would see that we're approaching -3 on our function. So again, since the values are not equal on both sides, then this limit doesn't actually exist because the function is approaching these different values. So again, we just say the limit does not exist. All right, now our last example we have right here. We have the limit as x approaches 3 of g of x, where g of x is defined as a piecewise function, where it's equal to 4x squared minus 3 for all values where x is less than or equal to 3, and is equal to x cubed minus 2x squared for all values where x is greater than 3. So if you would like to, you could definitely graph this piecewise function. However, we can also work through this problem just by the equations we're given. So since both equations define the behavior of the function as it approaches 3 from either side, we can use them to help us find this limit. Again, we want to find the value that we're approaching from both sides, so before and after x equals 3. So if we wanted to find what the function would be approaching from inputs that are greater than 3, then we would use the second equation that defines the function for all values that are greater than x equals 3. So this equation is continuous, so we can just use that direct substitution to plug 3 in for x, which would get us 3 cubed minus 2, 3 squared. So that would just be equal to 27 minus 2 times 9, 27 minus 18, which is equal to 9. So this is what the function is approaching from the inputs that are greater than 3. All right, so now we would have to find what the function is approaching and what the behavior of the function is for all the values that are less than 3, and what we would be approaching as we get closer and closer to 3 from the inputs that are less than. So now we would want to use that first equation to substitute into. Again, it's a continuous equation, so we can just use that direct substitution. So we would say, which would be 4x squared minus 3, so we would plug 3 into that. 4 times 3 squared minus 3, which is just equal to 4 times 9 minus 3, 36 minus 3, which is equal to 33. So again, we're seeing that the function is approaching 2 different values on either side of x equals 3. So when x is greater than 3, we're approaching 9. but when x is less than 3, we're approaching 33. So even though we don't see the jump discontinuity because we don't have the graph, we can see it in these values right here. Again, we're just going to say that the limit does not exist because these values are not equal to each other on either side. So we can just write here, does not exist. All right. So I hope this video was helpful. These are just some cases where you're going to find that the limit is undefined or does not exist. Please comment below any questions or video requests you have, and make sure to subscribe to keep up with the rest of the calculus series and our other STEM content.